Now, if you're a similar age to me, these sounds will be very familiar. It certainly takes me back to my childhood. I particularly remember the change in tone when it switches from loading the bytes of the image, the individual pixels, to the color information. So, what are we up to? And obviously, PCBWay, channel sponsor. This nice full color PCB came from them. There's a link in the description. Check them out. I've used them for my PCBs, and so far, they've been great. So, what are we doing? I thought it might be fun to take a step back in time and have a look at old school tape loading on my Spectrum board. So the ZX Spectrum tape loading is pretty interesting. So if I switch over to the oscilloscope, let's have a look at what's actually coming in on the signals. So I think channel 2, channel 1 even, is connected directly to the audio jack of my Mac. So let's just get that in screen. So what we start off with when we're loading a tape is a bunch of what they call pilot tones. So these are alternating high and low signals that are 2,168 CPU cycles, which is just under 620 microseconds. So in total, each tone should be 1.2 milliseconds long. And then we have the data bits, and a 0 bit takes just under 489 microseconds, and a 1 takes 977 microseconds. So on average, we have an amazing bit rate of 1,364, or around 170 bytes per second. So loading a 48K game takes just under 5 minutes. Now that's enough time for a cup of tea. Now actually finding a cassette player is pretty hard, so I am just using my laptop, and I've got a headphone jack connected up to a breakout board. So we've seen the signal. Now one of the issues is, if we run this again, it is quite loud, but let's run it again. What you can see is the signal goes positive and negative. Now, that's kind of fine if we were using a standard A to D converter, but we're feeding this straight into our ESP32, and it can't really handle negative voltages. So what we need to do is shift up the signal so we can actually feed it directly into the ESP32 ADC. So let's build a circuit to do that. So I've jumped into Circuit Lab. This is becoming my new favourite way of simulating circuits. It's really easy to use. I used to use KiCad and Spice, but to be honest, I cannot remember how to make it work. So I found this tool, and it's quite a bit easier. So what do we need to do? Well, let's have an input signal. So we'll get one of these voltage sources. This will give us a 1 volt amplitude sine wave at 1 kilohertz. So that will do for that. And of course we need our power supply. So we've got 3.3 volts. So the easiest way to shift this signal up is to use a resistor divider. So we'll just have let's use a 1K resistor. So that's the top one. And here's our bottom resistor divider. And we'll connect that up to our voltage plus side, so that'll be 3.3 volts at the top. Connect that down. Of course we need a ground at the bottom, so let's hook that up. So here we should get half of 3.3 volts, so around 1.65 volts I think. So let's connect the bottom of this to ground and the bottom of this to ground. And the only thing we need now is a DC blocking capacitor, so we'll stick a capacitor in here. Connect that to the middle of the voltage divider and this end to our voltage source. So let's simulate this and see what it does. So what we can do is we can do a time domain simulation. What we need to do is add some expressions. So let's do that. So we need some node names. So we've got our input voltage and we've got our output voltage. So let's run that now. So time domain analysis. So we want to do voltage on the input and we want voltage on the output. So I'm just going to start from 0.1 seconds so that we've got time for the circuit to stabilize. We'll run for 10 milliseconds, and our time step, what's this going to be? That's like 10 microseconds, I think. So let's run that. So there we go. What have we got? On our input, we have our input signal, which is around 0 volts. It goes up to 1 volt, down to -1 volt. And here's our output signal. So this is perfect. We go up to around 2.6 volts and down to around 700 millivolts. And we're oscillating around 1.65 volts. So that's perfect. Actually, what have we got? Yeah, I'll tell really, 1.6 volts. That's close enough. So that's great. We've shifted our signal up into the range that the ESP32 can accept. What happens if we go a bit crazy? We turn our amplifier up to number 11 and feed in a really high voltage. So let's run that simulation. And now we've got a bit of a problem. So our input signal is fine. It's doing what we asked it to. It's from -11 up to 11. But our output signal is now going up to around 12 volts and down to -8 volts. So it's highly likely this would really damage our ESP32 inputs. So let's deal with the negative signal. So the easy way to deal with that is to just add in a diode to block negative signals. So we'll just stick in a diode here. We want that to actually join, so let's wire that up again. So there's our, stop jumping over. Right, let's try that again. So we want that connected to there, and we want that connected to there. Perfect. And then we want our output on the output of that. And the only thing we need is a pull down resistor, otherwise this will just float around when it's negatively biased. So let's put in we can have a fairly high resistor for this, so let's just use a 10K. So wire that up. And now let's run our time domain simulation. And there we go, that's perfect. So when this signal goes negative, it clamps it at 0 volts on the output. But we've still got this very high voltage, which could make its way into the ESP32. So a simple way to deal with that is just stick a Xenia diode on the output, and that will clamp that. So stretch that across and wire this up. And I know I've got a 2.8 volt Xenia diode, so I'll just change that to match what I have in my bucket of bits. Oops, I made a mess of that. So neaten that up. There we go, that's better. So now if we run this, so run our time domain analysis, so that's perfect. So now we're clamped at 0 volts and we're clamped at around 2.8 volts. So even though we're feeding in this massive signal, it shouldn't damage our ESP32. Now the only thing I might do is let's go back to our nice sensible 1 volt. If we run this time domain simulation, then you can see that we're no longer centered around half of 3.3 volts. So we're now more like around, I guess around kind of 1 volt or 1.1 volts. And the reason for that is obviously we've got the voltage drop across this diode. What we can do is we can just change this top resistor value. So if we make this smaller, and now I'll run the simulation again, then I seem to have messed that up big time. So what have I done wrong here? Got 470K, so that's not right. I want 470 ohms. So let's try that again and run our time simulation. So there we go. Now we've got our nice input waveform -1 to 1, and on the output we're back centered back around kind of around 1.6 volts, sort of half 3.3. So that's perfect. We can feed that straight into the ESP32 and use the analog to digital converter. So let's jump over to the workbench and see if reality matches up to the simulation. So I've made up the circuit on breadboard and I've hooked up my signal generator to it so we can give it a bit of a testing. So let's look at the oscilloscope and we'll see how well this works. So turn on the signal generator. I've currently got it set to 1 volt peak to peak, and if we look down here we can see the yellow is the input, so voltage peak to peak 1.12, and our output is the blue one, getting 1 volt on the output, and its midpoint is 1.25 volts, and we can see it's not going negative and it's not maxing out the input either. So let's bump this up. So that's 2 volts, that's 3 volts. So you can see now we're clipping the negative, so we don't go negative. Let's go 4 volts, 5 volts, 6 volts, 7 volts, 8 volts, 9 volts. So our peak is being clipped. So that's it's around 3 volts. So that's pretty good. Let's keep going up. So now my input is at 20 volts, and I've maxed out what my signal generator can do. And our input voltage, 3.5 volts, I think. Let's have a look. So our V peak, that's coming out as 4 volts, it says there, but actually 1, 2, 3 and a bit. I think it's taking this slight negative spike into account and doing the total. So that's really good. The circuit actually seems to work. Brilliant. Let's try it out. I mean, you'll have seen it already because I've shown this at the start of the video. But let's try loading some tape data into the emulator using our amazing circuit. So I've got everything hooked up. Let's try loading. So you can see we've shifted the signal up. It's working really well. It never gets old looking at these screens being displayed. The way it builds up, I mean, you can see how the crazy layout of the ZX Spectrum screen memory is. It's really annoying sometimes trying to work with this screen, drawing sprites, and actually turning this into an image for the TFT screen. It's quite a lot of work. So the circuit's working really well. Now obviously there's other ways to do this. There's many ways to skin a cat. I could have used some kind of transistor amplifier or done something else, but this actually works really well. Now obviously this isn't the ideal way of doing it. There's better ways to do this. So what we can do is load these TAP files or TPZ files directly. So if we go into games, I've got a few tape files already stored in here. I think I've got Night Law somewhere. So let's find Night Law. There we go, Night Law. This is quite an interesting one because it's actually a accelerated tape reader. But you can see when we're loading using directly into the system, we're loading it at super fast speed. So this is running about 4 times the speed of what would be happening with sort of native audio input. You can just see how fast that screen loads to see how quick this is. Now obviously with Z80 files, they are just complete snapshots of the memory and they load pretty much instantaneously. But if you want to get all the kind of loading effects and see the nice loading screens, then TPZ files and TAP files are the way to go. And you get to re-experience some of the nostalgic excitement of loading a tape and seeing the flashing borders. But this is almost finished loading already. Normally that would take a few minutes to load, but it's loaded in the time I've been rambling on and talking to you. So any second now it should finish. And there we go. That's Night Law loaded. Fantastic. So check out my ESP32 Rainbow. It's on Crowd Supply right now. Please back it because we're almost fully funded and I need to get into production. Thanks for watching. I'll see you soon.